Thanks everybody for coming out. Take out your cell phones, because I'm going to show you something. I'm going to be talking about something that you can look up in real time on your phone. I want you to, when you open your phone, I want you to go to your internet search bar and type in AESO and then space CSD. AESO space CSD. What that stands for is Alberta Electric System Operator Current Supply and Demand Report. And since we're going to be talking about electricity supply and demand tonight, and since that web page provides real-time information, I thought I would show you. Lots of people got that? Okay, well, if you go up into the upper left-hand corner of that web page, below where it says Current Supply Demand Report, you'll see that in real time, Alberta total net generation is 9,983 megawatts. The net actual interchange is 33 megawatts, which means we're exporting 33 megawatts of power. Alberta internal load is 9,950 megawatts. And if you scroll to the right a little bit, you'll see a couple of columns. One says gas, hydro, energy storage. Right beside that, it's got an MC number, which stands for the maximum capability of the generator. To the right of that, it's got a column called TNG, which stands for total net generation. And beside that, it says DCR, and it's got some numbers under that. Right now, solar has 176 megawatts out of 1,663 megawatts of installed capacity. And wind is at 2,194 out of 5,340. No, the TNG is the output of the unit, basically, and we'll leave it at that. There's a slight technicality. DCR stands for Dispatch Contingency Reserve, and I'm going to talk a little bit about what Contingency Reserve is and why we need it, and why we need even more of it now that we're getting into higher levels of wind and solar. I think this is kind of a neat background image. It's quite a storm brewing, and I think it's apropos in two ways. First of all, we have to build power systems not to deal with average weather conditions, but with extreme weather conditions. And as far as the storm goes, part of the reason that I'm here tonight is that we're having to make some pretty significant changes to the existing energy market in Alberta to accommodate the increasing levels of renewable generation, particularly wind and solar in the province. What does net zero mean? It means that we have a system that's not adding greenhouse gases, primarily carbon dioxide, to the atmosphere. Net zero electricity means our electricity system is not doing that, but our building and transportation systems are. So what some have proposed is that electricity be net zero by 2035 and the rest of our economy be net zero by 2050. I know the Alberta government and the federal government are still having some to and fro on what the actual deadlines are going to be, and we'll see how that evolves over time.
Why is that necessary?
Why is it necessary?
It's not necessary.
Let me answer your question near the end of the presentation, okay? All right. I'll give you my thoughts on it. So I took you to that web page because it shows electricity supply and demand, and that's really a lot of the focus of what I'm going to talk about tonight. So electricity supply comes from large-scale generators. We used to have coal plants. We don't anymore. We've got large natural gas generators. We've got smaller natural gas generators. We've got distributed generators, including rooftop solar, and we've got imports from British Columbia, Saskatchewan, and Montana. Those are our sources of supply. Demand, really that's consumption. Domestic consumers, many different classes of consumer, residential, commercial, industrial, you know all the classes of consumers. Exports, when we send power to other jurisdictions, that's like a load on the system. And also, whenever you push power across a transmission system or a distribution system, there are losses in the system, and they have to be accounted for. So I'm going to spend a little bit of time on this slide. Here are some of the major challenges. The first one is maintaining electricity supply-demand balance given the increasing penetration of intermittent generation. And I'm going to spend a bunch of time on supply-demand balance because it's absolutely critical in an electric power system. Second part is establishing the right conditions for dispatchable generators to stay in business. Now, a dispatchable generator is one that I can control the output of. I can say, I want you to go to 50 megawatts or 75 megawatts or back down to 40 megawatts. A non-dispatchable generator is, it kind of puts whatever amount of power in is available. Wind is an example of that. Solar is an example of that. When cloud moves in front of the solar panels, the generation drops, and we have to be able to accommodate that. Another major challenge to achieving net zero, and I'll only touch on it briefly if there's time, is electrifying transportation and building energy systems. As part of all of this, we have to increase the generation, transmission, and distribution infrastructure. I'll talk about those words in a minute. Getting everything that we're told that we have to build designed, approved, constructed, and commissioned in time is going to be an enormous challenge, and that challenge could be a session like this all on its own. There are reports out there about simply the amount of material that we would need to accomplish net zero by 2050, and the numbers are truly staggering. And of course, as an engineer and part of the electric utility industry, I'm mandated to try and help all that take place while making sure that electricity is still affordable, because if you can't afford electricity, it doesn't matter whether it's reliable or not. Just a very quick overview, very schematic overview of the electric power system. Transmission connected generators, have represented them as circles. Again, they're the coal plants and the gas-fired power plants that put power into the transmission system. Power flows through the transmission system into distribution systems. The City of Calgary has a distribution system. The City of Edmonton does. The Town of Cochrane, Red Deer. So the transmission is for large amounts of power. Distribution systems are more local, and then distribution connected loads, that's your house, your corner store, your shopping centers, that kind of thing. That particular plant over there is called the Crossfield Generating Station. It's got 3 what are called aeroderivative gas turbines, and they provide about 150 megawatts. So 2 very, very critical facts about power systems, and I would urge you to keep them in mind as we go through, because really this first one especially is the focus of the presentation. Supply and demand on an electric power system have to be kept in sync on a near instantaneous basis all the time. If you get out, even if you lose a generator and you're not prepared with protection and control systems, you can black out the entire system in a matter of less than a second. And so it's very, very important. And the biggest challenge that we face today going forward is going to be to maintain that supply-demand balance in the face of the variability that renewables bring to the system. Another point is, you'll hear things like this wind turbine or this wind plant or this solar farm can power 10,000 homes. Well, no, it can't. Not really, not on its own. And the reason is, for solar, it's obvious. The sun goes down at night. So wind and solar need the rest of the electric infrastructure, and they need dispatchable generation. Right now, wind and solar need fossil fuel generation or they don't work. So I'm going to talk a little bit about demand. So what you see in front of you is a graph. There's 2 days on there. The top line, I did it again. The top line here, this is a 24-hour day. This is the demand in megawatts. That's the amount of power being consumed in Alberta. 3 o'clock in the morning, it's relatively low. It ramps up in the morning with human activity. It stays fairly constant during the day. And in the evening, in the winter, it ramps up again. The sun starts going down, lights come on, people go home, start cooking dinner and that kind of thing. And that load profile is fairly standard. Summer is a little bit different. The red line, it ramps up in the morning and ramps down in the evening with human activity. It's a little more steady during the day. It tends to follow the heating load. The sun goes down later, so it doesn't have that same pronounced peak. If you look at a week, you can see the daily pattern each day, winter higher than summer, but the pattern is repeatable, it's consistent, which means we can do a reasonably good job of predicting it. What you see here are on-peak periods and off-peak periods. That's the reason I point that out is because we're told that in the future we'll be able to use off-peak pricing when electricity is cheap to charge our electric vehicles overnight. And we'll get up in the morning and we'll be able to drive off to work and we'll be able to make use of lower prices. You'll see that that's not really going to be the case. If you look at it over a longer period of time, here's the period from 2015 to 2024. It's fairly consistent. You see the winter demand is pretty high. Spring and fall are lower. That's when we try and maintain a lot of our power plants. And in the summer, when we get the heat waves and that kind of thing, the demand goes back up. So those patterns are pretty consistent. And as an engineer, and not me personally, but power system operators, power system engineers understand that pattern. And again, they have to keep the supply in balance with demand at all times. As an engineer, I'm a fan of graphs. If I put one up and I will try and explain in words what it means, but if I don't do a very good job, by all means, put up your hand and I'll try and explain it. But all we've done here is we've taken the demand for an entire year and just sorted it from highest to lowest. And so the lowest demand was 8,110, the highest was 12,193. One of the reasons engineers use this kind of graph is because it tells you something about how often the load is at a certain level. So if you follow this white line here, you can see that 47% of the time, the load is at or above 10,000 megawatts, and the rest of the time it's below that. And I'll provide an example of how we use that a little bit later. It's called a duration curve, and you'll see that in a couple of different contexts. So where have we been? This is a pretty noisy chart, but I'll point out the main points. These are Alberta's energy sources between 2015 and 2024. The blue on the bottom, that's Alberta's hydro resources. We've got just about 900 megawatts of hydro. It's been pretty static. Alberta doesn't have a lot of hydro resources. We don't have a lot of big river systems like they do in eastern Canada. So that's one of the things that constrains our ability to go green, if you will. Speaking of green, this next one, that's our wind output. The red line just above that is a biomass. So we have, because we have some forestry in the province, they can burn wood refuse and create power that way. The yellow, solar, there's not a lot there, but it has grown dramatically in the last period of time. This is coal. As you can see, we used to get a lot of our energy from coal-fired power plants. That's tailed off, and in fact, the last coal plant retired just in June of this year. Natural gas has filled in a lot of the gap. This green here, that's what's called behind the fence generation. One of the things that makes Alberta unique is it has a very high proportion of industrial load. I pointed out the total net generation. One of the reasons why all that generation doesn't necessarily show up on the grid is it feeds industrial loads that are on site. It's called behind the fence generation. And then the purple are the imports mostly from British Columbia. That's the largest intertie. Yes?
So, all grid.
Well, behind the fence doesn't necessarily talk about a technology type, but what it means is that I've got in a classic scenario, I've got a generator and I've got a load, and they're right next to each other, and that load might be an industrial load that needs process heat. And so I run a generator that produces, like a cogen facility can produce both electricity and steam. So I'm running it, I'm providing the steam and the power to that on-site, but I'm still connected to the grid. And the reason a customer would want to do that is because sometimes that generator will go down and they need backup power from the main grid. But behind the fence doesn't necessarily specify a specific technology type. Okay, so this is just a summary of what I talked about. One of the interesting things is the Alberta government, I think it was in about 2015 or 2016, gave some subsidies, if you will, to coal-fired generators. Some of the coal-fired generators have retired, some of them have converted to gas. But what I find interesting is that we retired about 6,300 megawatts of coal. China has 1.15 million megawatts of coal. Since we started the process of retiring the coal-fired power plants in Alberta, the world has built roughly 630,000 megawatts. So 100 times what we retired has been built in other parts of the world. Now, about half of that has been retired, but the fact is that since Alberta embarked on a transition away from coal, the world has built an awful lot of it. This is it used to be British Petroleum published this report. It's now, I'm sorry, this is Our World in Data. So this is the energy mix in the world as of 2023. You can see here about 78.5% of, 76.5% of world primary energy in 2023 came from coal, oil, and gas. That's down from 78% in 1983. So we've gone down 2% in about 40 years after having spent several $1 trillion on renewables. So that's a challenge to those who are proponents of renewables, of course. They would like to have seen that number come down significantly more. The fact is that a lot of the world still relies on fossil fuels, and you can see, here we look at carbon dioxide emissions. The blue at the bottom are the OECD countries excluding Canada, carbon dioxide emissions. The red are Canada's carbon dioxide emissions, and the green are the non-OECD country carbon dioxide emissions since 1990. So the OECD and Canada emissions are going down slightly, the rest of the world going up. So right now, as of 2023, Canada emitted 1.5% of the world's carbon dioxide emissions. So I'm going to switch now. I'm going to start talking about, so that gives you kind of the big picture of where Alberta is, and hopefully I've put that in the context of how Alberta fits into the rest of the world from an energy standpoint and an emissions standpoint. So I'm going to start talking now about the characteristics of renewable generation. I'm really going to focus on wind and solar because that's where Alberta is headed. Wind generation, it has a near zero variable cost. In other words, once you build it, it runs pretty much for free because there's no charge for the wind. There's obviously no carbon dioxide emissions at source. There are when we build the components. Obviously, wind is weather dependent, and I'll talk a lot about that. It's located far from loads, so we need transmission lines to get the power to where we use it. And it's non-dispatchable, and I mentioned that earlier. One of the characteristics of wind is that it shows up when Mother Nature says it's okay to show up, and it doesn't show up when Mother Nature says no. And we don't have a lot of control over it. We can limit wind ramps going up a little bit. If there's too much wind, we can curtail. But generally, you don't like to do that because wind is generally, at least in one sense, it's free. You're not burning fuel. So here's a graph, and again, I hope you like graphs, but here's the top one is the Black Spring, the output of the Black Spring Ridge wind farm for a week in January. And you can see it was up around 300 megawatts, dropped suddenly to 0, back up to 200, back down to 0, back up to 300, stayed at 300 for a couple of days, dropped very quickly to 0, and stayed at 0 for the rest of the week. This is McBride Lake. All of this data, by the way, is available publicly. There's nothing here that's secret. So McBride Lake, a lot of variability, wheatland. You might think that with a large number of wind farms that it spreads out the variability and it would be reasonably steady in total. That's not the case. As you can see here, the total generation in this period of time, up around 2,000 megawatts, down to 0, back up to 1,500, back down to 0. And that's when wind was had considerably less capacity. So this is one of the challenges that power system engineers are facing now, is how do we integrate into our power system that, again, must remain balanced at all times, this kind of variability. Seasonally, not only is wind very erratic, highly variable over the short term, it varies seasonally. You're all familiar with Chinooks, and so if you look here, wind output tends, oh, I should talk about capacity factor first. Capacity factor is really like a percentage. If my generation is a 50% capacity factor, I'm producing 50, and my maximum production is 100. And you can take that over a short period or a long period. So you just think of the capacity as your percentage output. So in the winter, we tend to get wind up in the 50 and 60% capacity factor range for a month. In the summer, it's down around 20%. So that means in the summer, the wind is only producing 20% of its nameplate capacity. So this is a plot, and I'll explain this one a little bit. Along the bottom here, we have demand, and as I move from left to right, the amount of energy being consumed by customers is increasing, right? So there's more customer demand here than there is over here. It's increasing in this direction. This is the capacity factor of wind during these periods of time. So, for example, this point here, the customer demand was just over 11,500 megawatts, and the capacity factor was 30%. Your question?
With regards to wind versus summer, winter versus summer,
Yeah.
does that have anything to do with density?
It has more to do with the wind regime. There's a lot more wind in the winter, especially Chinooks. I have a graph that will show you exactly what I'm talking about in just a minute here. The fact that those points are scattered all over the chart really says wind could be anything when I have high demand. And what that means from an engineer's perspective is I can't rely on the wind being there when load is high. It might be, but it might not be. And that's one of the inherent characteristics of wind and solar generation. Solar is a little bit different, and I'll get to that, simply because the sun goes down at night. So here's exactly the graph that you were just alluding to. So along the bottom here, this is the temperature, the ambient temperature, and for that I just used the temperature in Calgary International Airport. And here's the median output, call it the average output of wind as a function of temperature. So we get really high wind in the winter when the temperature's around 5 degrees. Well, guess what? It's when Chinooks blow in that raise our winter temperatures to in the 5 to 10 degree range that we get a lot of wind on the system. But when it's minus 30 in the winter, we don't get very much wind at all. And when it's plus 30 in the summer, we also don't get very much wind. And so I mentioned in one of my first slides that we have to build power systems to handle extremes, which means we really have to plan power systems as if there's no wind at all. Okay? So in some sense, you have to have two power systems because you have to have a separate one because the wind is not always going to be there. I'm not sure how I'm doing for time, Michelle.
We've got time.
Oh, okay, yeah.
I got a question to the wind generation graph. Excuse me. How repeatable is that pattern?
What I tried to illustrate in the first few slides is it's statistically, it might be stable, but at any given time, you have no idea. Like just because it's 100 megawatts today doesn't mean it's 100 megawatts tomorrow at the same time. It's essentially random. All right, I'm gonna pick it up and get to I'll go through solar a little more quickly. Same thing, you often hear Alberta is a great place to build solar. Well, in the context of Canada, it is, but it's not great in the North American context. You can see down here in the US Southwest, no surprise to anybody, they get a lot more solar energy in a year than we do in Alberta. In the world context, there's Alberta there, and you can see that most of North Africa, South Africa, almost all of Australia, parts of Central Asia, and parts of South America get more sun than we do. So what that means is if I put a solar panel on my roof in Calgary and somebody puts the same solar panel on their roof in California, they're going to get more energy out of it than I am, which means my cost of energy out of solar for each kilowatt hour that I get into my house is higher. All right? So you can't use numbers that people come up with for places like California and apply that to Alberta, especially because of our climate. One of the reasons for the variability is this is the number of hours in a day. Here's a graph that goes from January to December. This is the number of daylight hours in a day. This line here, that's Quito, Ecuador. It's pretty much the same length of daytime every day. In Fort McMurray, it's a low of about 6.5 hours and a high of almost 18 hours. That introduces a seasonal variability that you also have to accommodate. If you're talking about solar, you're going to get hardly any of it in the winter, and you're going to get a whole lot of it in the summer. And believe me, getting too much solar, getting too much of generation is a significant problem, as is not having enough. This is weekly output of solar over a period of 3 years. This is the entire Alberta fleet. You can see that it goes up and down with the number of hours in a day. That's not a surprise at all. The daily pattern, simply because the sun rises higher in the summer, you're going to get average generation lasts longer and goes up higher. In the winter, you only get to a maximum of about a 30% capacity factor, and of course you have fewer hours in the day. Going back to the question about does the pattern repeat? Well, again, statistically it does in a sense, but here you have a sunny day, so solar ramps up, stays flat, and ramps down when the sun goes down. Here, it's all over the map. This is a cloudy day, or a scattered cloud. You get a lot of, oscillation. It goes up to the top, but there's a lot of oscillation as the clouds pass. There's a day where, middle of summer, but it's a rainy day and you don't get very much sun at all. And again, we have to deal with that. This is the similar graph I showed for wind. Again, at very high levels of load, you can't count on the sun being there, so you essentially plan as if you don't have any wind or any solar generation on the system, and then you use it when it's available. Hydro's a renewable resource, but it's also dispatchable, and in fact, hydro units are among the very best that we have because they're controllable, they're long-lived, they don't suffer thermal stresses because you're running water through turbines, so they're very reliable. But like all other forms of weather-dependent generation, they're quite variable. Summer, much higher. Spring runoff from the Rockies, we get water going through the river systems. Generation goes up. In the winter, it's back down. So you have to take into that. And so I guess the way I would put that is one of the primary tasks of our electric system is to protect us from the vagaries of weather, and what we're doing is building a power system that is subject to the vagaries of the weather, which is an interesting challenge for sure. This is a graph of droughts across the prairies for the past 600 or 700 years. We have droughts. So does BC. This is a recent graph of the water situation in British Columbia. So another thing I hear from renewables advocates a lot of times is, well, we'll just build a bunch of transmission lines to BC and we can trade wind for water. Not always, and in fact, only in 8 of the last 15 years, BC Hydro has been a net exporter of electricity. So I'm going to move on to battery energy storage systems. This is called an eReserve 3. It's a 20 megawatt facility. People talk battery energy storage systems a lot and they give you the megawatt number. Well, that doesn't tell you much because how much storage does that have? This one has 35 megawatt hours, so it's about 1 3/4 hours. And if it injects into the system for 1 3/4 at its maximum, it's done, and you have to recharge it. To match Alberta's peak generation in 2024 so far, it would take 6,800 of these systems. Now, I'm not going to explain this graph too much. I'm certainly happy to explain it in the questions if anybody's interested, but this is a way of just estimating how much battery storage we would need to run Alberta just on wind, solar, and batteries. And I'm not suggesting that anybody would try to do that, but some people say that we should be able to do it. Well, the cost of that would be about $2 trillion, which is $100 million a day for 55 years. It's out of reach. And so battery systems, don't get me wrong, they have their place. They are very, very good providers of certain services because they're very quick and they can, they really do help balance supply and demand in real time. So there are very good uses for batteries, and so, I would never criticize them. But there's no really economic long-term storage of electricity like there is for, natural gas and oil and stuff like that. Now, net demand is the consumer demand minus all of this variable generation. And remember, that's what we have to balance. As engineers, that's what we have to balance. And there's a number of ways we can do that. But just to give you an idea of how variable it can be, these graphs show 6 weeks of actual demand in 2022. This is what it looked like after we subtracted the renewable generation, and this is what it's going to look like in the future. And I can tell you that that is a lot easier to manage than that. This has on-peak and off-peak periods. This doesn't. So this is where we're headed, right? This is what power system engineers are now faced with managing as we go forward. There's the demand. That's how much energy consumers want. And this is a hypothetical generator that produces the 5,000th megawatt in the stack. So if I stack all my megawatts up from 0 to 10,000, this blue line here represents the 5,000th megawatt. This is a bit of a back of the envelope exercise, but it does produce meaningful results. So what happens when I put more renewables on the system, I interrupt that blue line. And those gaps are where I have to either shut that generator off or I have to run it at no load. Okay? And by the way, I should have mentioned that these blue lines represent dispatchable generators, because if they were non-dispatchable, those lines wouldn't be straight at all. So here I've got even more renewables. What you notice is that my 5,000th megawatt generator isn't needed nearly as much anymore. And the times when it starts and stops are more random. Well, that's a problem, and I'll get to that in a minute. My 2,000th megawatt generator so far is not too bad off. But now I've got so much wind and solar on the system that I've now interrupted that black line, or the blue lines, So here we see that the 5,000th megawatt generator is needed very infrequently, but it's still needed. The 2,000th megawatt generator, instead of having a nice smooth time of running, it's interrupted quite frequently. Now, if you think about your car, where you get your best gas mileage is when you're on the highway doing a steady speed. When you're stuck in traffic and you're stopping and starting and stopping and starting, your gas mileage goes up. That's because your efficiency is very much tied to hitting an optimal point and then running at that steadily. That's what baseload generators are good at doing, and that's one of the things that we're interrupting when we bring in a lot of variable generation on the system. So you see, I've circled spots where there's the zero line there. That's where net demand would go negative. Net demand cannot go negative. You can't use less than zero power. So what that means is during these periods of time, we're actually having to curtail or shut down wind and solar. And what that does is it means over the course of the year they have fewer energy sales, which means their cost per megawatt hour produced goes up. Here's a list of problems. First of all, we have generators that are interrupted a lot more, but they have the same fixed cost. Now, in a normal market, you would say, look, if I have a new competitor that outcompetes my old competitor, that's a good thing and consumers benefit. The only problem is that if the outcompeted generator goes away, your lights go out when it's minus 35. So you can't have that. This generator used to run steadily, basically for the whole year, other than maintenance periods. It doesn't do that anymore. Every time you stop and start a generator, you're stressing it because you've got thermal stresses as components heat up and cool down, heat up and cool down. They're less efficient because you've got, you're not operating at an optimal point. And obviously they're getting less revenue for each, or less revenue over the course of the year. So somebody asked me earlier about whether there's economics. Well, there's a little bit of economics, and this is what the cost curves for generators look like as a function of their capacity factor. Now remember, I said the capacity factor is essentially, you can think of it as the percentage output. So when my generator is producing at 100%, if I produce 100% of the capacity over the course of the year, my cost is low. That's when my cost is the best, because I have more energy sales over which I can pay off the mortgage and the fixed costs of my power plant. As wind and solar come along, and they're normally priced into the market at zero, so they are dispatched ahead of all the other generators generally, my costs start to go up. Because if I, for example, if I go to a 50% capacity factor, I only have half as many energy sales as I used to. I still have the same fixed costs, so I have to recover more for each unit of energy that I sell. And of course, when I get to very low capacity factors, the costs go up not linearly, but exponentially. And what's really strange is that some of the proponents of renewable generation say, well, that just proves that the renewable generators are really competitive because these guys' costs just keep going up and up and up. Okay? But they do. But it's being driven by the challenge of integrating the renewables. I'll skip that one. I'll skip that one. I could talk about energy emergency alerts. I won't spend a lot of time on it in this case. There was an energy emergency alert. We were asked to curtail consumption. Part of the reason, not the whole reason, but part of the reason was that wind and solar had just disappeared. And there are a number of examples of this. And I, at the risk of somebody telling me I blame wind and solar, that's not always that's not only the case. There are other issues, but they're interrelated, which is part of the reason why the balancing act is so difficult at times. You may recall back in January of this year, we were asked to curtail our demand. The ISO was having an emergency alert. At that time, we had installed capacity of wind of 4,481 megawatts, and we were producing 8 megawatts. So that just emphasizes the fact that, as I said earlier, we really have to plan power systems to be capable of operating when there's no wind and solar at all. When I asked you to open the web browser and I said there's that column called DCR. Well, DCR stands for Dispatch Contingency Reserve. A contingency is something that we know is going to happen, but we don't know when, we don't know where, and we don't know how big. So an example of that is lightning hits a transmission line, knocks the line out, and all the load behind it drops off. Or there's a boiler leak in a generator and they have to shut it down. We have to be prepared for those kinds of things all the time. And power system operators always set up the system so that the next thing that goes wrong, there's an automatic response to it. And I should say a combined automated and manual response. The first thing that happens is automated, and then this system controller will direct other generators to fill in where the generator just tripped off. So the ancillary services, I'm not going to go into details. Regulating reserves they're always there, and they follow the little ups and downs of demand as furnace motors turn on and turn off, escalators, elevators, all of those kinds of things. Spinning reserves and regulating and supplemental reserves, they're the things that have to respond when a generator trips off to fill in what the generator just gave up. Ramping capability, that's a brand new one. The reason that the ISO, Alberta Electric System Operator, who's the system operator, is talking about this ramping capability is for the very reason that I was talking about a few minutes ago, the very large swings that are possible in net demand as a result of the very large swings in the amount of renewable generation. So this is one of the adaptations that we're making on a go-forward basis to try and incorporate wind and solar and other renewables in an as efficient manner as we can. As engineers, I can say we don't make policy, but certainly it's our job and our obligation to everybody in this room to do what we can to integrate and make sure that the lights come on when it's minus 30. I mentioned to Michelle just before the start of this that electricity seems incredibly simple because you walk over to the switch, you flip it, and lo and behold, the lights come on. But the amount of stuff that goes on behind the scenes to make sure the lights come on makes electricity probably the most complicated commodity in the world, especially since you have no time at all. If, for anybody in the oil and gas industry, you have a certain amount of line packs. So there's a certain amount of time, for example, where you can withdraw more natural gas from a pipeline than is being put in because the pipe itself is a storage reservoir. We don't really have that in electricity. We have about 2 seconds worth of storage in most cases. What we're talking about in terms of integrating renewables is, the first thing is to create a day-ahead market and with day-ahead unit commitment. Now, what unit commitment is, it's making the decision to start a unit up when you may or may not need it. And the reason that that's important is if the wind drops off suddenly, I need to have a dispatchable generator that's there. But in order for that generator to be there, I have to have turned it on the day before. Some generators anyway. Some are long lead time generators, which means it takes 8 hours or so for them to warm up and be able to produce power. Other generators are quicker than that, and batteries, to the extent that they're charged, are very, very quick, and so they can be good resources. But whereas today, in the energy market today, a generator gets paid only for the power that it actually produces. When you saw those interrupted blue lines, if I'm a generator, I may have incurred $30,000 in costs to start my unit up, ramp it up, be ready to supply power, only to have the wind ramp up, have the system controller tell me I'm not needed, and I've eaten that $30,000. So that's a financial risk, and one of the ways that we're trying to address that in Alberta is through that day-ahead unit commitment. And what that means is when the system operator says, I want you to turn on so you're there tomorrow, I have some form of guarantee that I'm at least going to get my money back. And so that is, to do that, there are a couple of mechanisms, and in fact, we were in discussions today about these market design changes that are going on to help accommodate this. I talked about developing new ancillary services products, and the one that I pointed out was the ramping or load following. We haven't really needed that in the past because the swings in net demand over the course of a day, we could follow with the resources that we have. Those swings are getting much larger and much more rapid, and so we're going to need additional resources. So one of the ironic things is the more wind and solar we build, the more we need the dispatchable generators, but the more they're not producing energy. So, you know, in one sense we tell you, well, we need more and more of you, but we're going to pay you less and less. And so that's one of the challenges of designing the market. Now here's another one. One of the proposals is that we reduce the price floor to less than zero, which would mean that generators would pay to inject power into the system. Now the reason you need to do that, or the people are thinking about doing that, is the fact that if I've got 9,000 megawatts of generation and it's all offered into the market at a price of zero, and I've exhausted, my demand is all served and I got to start curtailing generators, I got to know who to curtail. And one of the ways of doing that, instead of dispatching up in terms of price as you normally would, you dispatch down. And you go into negative prices. And there are markets that have negative prices. Ontario had negative prices. I'm not as familiar with the Ontario market, but I know some number of years ago there was a report by the Ontario Auditor General. Ontario customers paid $5 billion to give free power to their neighbors. And that's certainly a situation that we want to avoid. And it's something that is, you know, front of mind for people who are involved in the current, it's called a restructured energy market, or REM. And the ISO is leading that. I was thinking when we originally talked about my doing this presentation, I thought we were going to be a little bit further along in the design process, but appreciate it is very, very complicated. The ISO is working very hard. I've got to give credit to people for trying very, very hard to make sure that not only do we accommodate that the renewable generation in the market, but that we do so in a way that, you know, the three-legged stool, is it reliable, is it affordable, and is it net zero? Another thing, and I'll just touch on it briefly, one of the challenges that we have right now is that when wind and solar does this kind of oscillation, it doesn't cost anything. They don't pay for the ability to do that. In fairness, other generators don't pay for those, all of the services, all of the ancillary services that are necessary to maintain supply-demand balance in real time. Generators don't pay for that. So one of the things that the Alberta government is currently considering is making a change to the transmission regulation to make generators at least partially responsible for things like the variability that they bring to the system. What that can do is encourage generators to perhaps build on-site dispatchable generators or on-site batteries so that what they present to the electricity market is a little more stable. Super quickly, I'm going to just touch on electric vehicles. Alberta has an interesting climate because it can be very cold and very hot, and what happens with electric vehicles is as the temperature drops, the charging is less efficient, so it needs more electricity and more infrastructure, and also batteries don't last as long. The other problem is as the temperature drops here, over here, the temperature dropping down here, the range of your electric vehicle drops, in this case, to around half of what it is. So you're having to recharge those vehicles more often in Alberta than you would, say, in Vancouver. So one of the things I said earlier is don't take something about solar from California and say, oh, we can do that here. Same thing with electric vehicles. I'm still not sure how we're going to solve the problem that most people don't, or many people don't have garages in which to park and plug in their electric vehicle chargers. Certainly not by 2035 or whatever the mandate is. I would like to see a community of substantial size, like 50,000, say, okay, we're going to be the guinea pig for net zero, and see if we can make it work there before we try and apply it to the entire country. But that's above my pay grade, as they say. I just work here.
I have a suggestion.
Yes.
That should be Ottawa.
Heat pumps. Heat pumps are interesting. They're very efficient. So over the course of a year, you will use a lot less energy if you use a heat pump than if you use a natural gas furnace. There's one little problem. When it is, very cold, heat pumps lose their efficiency, and eventually it gets so cold they just shut down. And when you do that, you have to have either an electric or a natural gas backup. So even if everybody in Alberta switches to heat pumps, we have to make sure that we can supply heat in the form of electricity. Now, how big is that? Well, this red line here is for 2012 to 2022, the red line here, that is the total electricity use in Alberta, all customers, shopping centers, hospitals, everybody, except the behind-the-fence industrial customers. The blue line is the average per hour energy delivered to residential customers using natural gas. Just residential customers. So if we have to replicate the heating load at -30 when all the heat pumps have shut down, we need a power system that's twice as big as what we have. And that's just for the residential heating load. And that just shows you, and I skipped over that slide, but that shows you that Alberta uses a huge percentage, gets a huge percentage of its energy from natural gas. And that puts it in a class different from the other parts of the country. And so one of the challenges is, and even the Canadian Electricity Association came out and talked about this, is we need a regional approach to net zero. One size doesn't fit all, and when you have this much reliance on natural gas and transportation fuels as Alberta does, you're not going to flip this on a switch, okay? Now, I was asked a question in the beginning, why are we doing this? and I talked, I'm a fan of Friends of Science because I'm a friend of science. And I'll tell you a little bit about a personal experience. We'll explain some of the slides, but you are all aware of the Jasper fires recently. Well, my stepdaughter was working at the first building in Jasper to burn down during those fires, and we were supposed to go to Jasper the day that they closed the road. We were going to go up and visit Tammy. And we checked the road report, and the road was closed, and Tammy had to drive through Kamloops and come back into Calgary, 12-hour drive. Terrible, terrible tragedy, terrible loss of a beautiful town. We took many trips there. But one of the things that Holly and I talked about on the way there was how the trees had suffered badly from the pine beetle. And we said, you know what, this is a problem. Well, of course, as soon as the fires hit, it's like, well, of course it's climate change. All right? So it doesn't take long, it wouldn't take long for journalists to do a little digging on that issue as opposed to just repeating what they've heard. So I thought I'd take a look at carbon pollution. You've all heard the term carbon pollution. I won't mention who likes to use that term, but somebody likes to use that term. Well, at 150 parts per million, anything below that, plants start to die, and the rest of us go with it. The current level, there's an observatory at Mauna Loa in Hawaii where they measure carbon dioxide. It's 422 parts per million, which means 4 out of every 10,000 molecules in the atmosphere are carbon dioxide. And when you ask people, some of them say, well, it's got to be 20% or 30% or something like that. It's not. It's 0.04%. 800 to 1200 parts per million. That's what we pump carbon dioxide into greenhouses to make plants grow. Remember, this is pollution according to some. The heating ventilation standard, 1,000 parts per million in a room. The National Institute of Occupational Safety and Health in the United States, 10-hour exposure limit, 5,000 parts per million. The 15-minute exposure limit, 30,000 parts per million. Headaches and slight impairment at 50,000. Human breath is 40,000 parts per million of carbon dioxide. So you can make all the arguments you want about, you know, what impact carbon dioxide is or isn't having on our climate. And by the way, there's a lot more than one climate in the world, and I'll get to that in a minute. But calling it carbon pollution in my mind is just it's fear-mongering, and it's not responsible. I have no problem with wind generation. I have no problem with solar generation. I have no problem with incorporating all kinds of sources, but at least let's have an honest discussion about why we're doing it and what the costs and benefits are. I'm a great believer in consumer choice. If somebody wants an electric vehicle, by all means, go ahead and get one. But don't come and tell me that I have to pay you to buy an electric vehicle because that's going to save the planet. Anyway, there's a very interesting table 12.12 in the IPCC Working Group 1. The IPCC, of course, is the Intergovernmental Panel on Climate Change, a body of the UN. And it's interesting to see what happens between the working group and the politicians. But the purpose of this slide is the color codes. So here we have high confidence of an increase in some value or other. Here's a medium confidence. Here's low confidence in direction of change. So anywhere you see a white box, the IPCC doesn't see any change in the climate based on either the past or the projections into the future. So let's see what that tells us. Well, it tells us that snow, glacier, and ice is not getting worse. Snowfall is not getting worse. Hail is not getting worse. Avalanches are not worse. There's no change in relative sea level rise, no coastal flooding, no coastal erosion. There is some confidence in ocean temperature. There's no change in, or even expectation through, by the way, the year 2100 for marine heat waves, ocean acidity and salinity. I'm not gonna, there's some indication that there's increases and decreases in that. But here's for me, fire weather, no change. So you hear constant drumbeat in the media that our forest fires, as tragic as they are the result of, I think one politician said that when you go on vacation in your family car, you're causing forest fires. Well, even the IPCC sees no increase in fire weather. They see no increase in agricultural drought, ecological drought, hydrological drought, aridity, landslides, heavy precipitation, river floods, or mean precipitation. They also see no increases in wind speed, severe windstorms, tropical cyclones, including hurricanes, and sand and dust storms. So even the UN IPCC says, yes, according to the IPCC, there is a heat effect, and that's to be expected because the temperature of the planet is going up. And as I said, it wouldn't take a lot for our journalists to take a look at some of this stuff. To look at forest fires. Here's the graph of forest fires in Canada. Remember how climate change is causing them to increase? Well, except they're decreasing. The hectares burned, 2023 was a very bad year. 5% of about 347 million hectares. That's a bad year. Thing is, it's better than it used to be. This is a paper by some university researchers I won't go into detail, but all of these numbers show what the burn rates in our forests were back into the 1700s. They were all higher than they are today. These are the areas burned by wildfires, a great source if you're ever looking for data, Our World in Data. In every region, since about 2000, the acres burned due to wildfires has been going down. The world as a whole, since 2000, acres burned due to forest fires, due to wildfires, has been going down. And I think the biggest frustration for me is the fact that this information is out there, and why don't we have an honest conversation about what we need to do to make our world a better place, instead of the kinds of stuff that just repeat stuff that doesn't make any sense. We talk about, you hear about, our food crops are in danger. This is a graph since the 1960s of the crop yields, number of bushels or kilograms of crop that we can get off each hectare of land. They've all gone, in the worst case, they've stayed the same. Most of them have gone up. This is I found a really interesting graph. The green area here is the amount of population supported without synthetic nitrogen fertilizers. This is the population supported by fertilizers. So governments around the world tell us that we need to cut back on fertilizers. Well, guess what that means for half of the world's population? We are told that heat kills, and it can. Here's a graph. This is from the Statistics Canada website. This goes from January to December. This is the weekly weekly deaths in Canada. You'll see that they are noticeably lower in the summer. I'm not attributing that to climate. I'm not attributing it to climate change or anything like that. But, again, we're all going to die because of heat. As tragic as heat deaths are, that's not the case. And I guess I would point out that the best counter to heat deaths is air conditioning, which requires a reliable, safe, and affordable electric power system. One last graph. This is number of deaths from natural disasters. You see your chance of dying in a natural disaster in 1920 was a heck of a lot higher than it is now. All right? That's a combination of things. We have satellites, we can detect storms, we have fossil-fueled vehicles that allow us to get the heck out of the way of bad storms and that kind of thing. Anyway, the three-legged stool, one of my jobs, at least until I retire, is to try and bring all of this together so that the lights stay on and that we incorporate this and to do that in an environmentally responsible and sustainable way. But above all, to make sure that people can afford electricity, because they really do need it.